Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is Lesson 6, Exponential Growth, U.S. Population and World Population. So the classwork says Mathematical Modeling Exercise 1. Callie and Joe are examining the population data in the graphs below for a history report. Their comments are as follows. Callie said, "It looks like the U.S. population grew the same amount as the world population." So here's the U.S. population, here's the world population. The graphs look similar. But that can't be right, can it? Joe says, "Well, I don't think they grew by the same amount, but they sure grew at about the same rate. Look at the slopes." So A says, "Is Callie's observation correct? Why or why not?" So she thinks they grew the same amount from the years 1950 to the year 2000 and 1950 to the year 2000. The graphs look almost identical. Well, it is not true. The answer is no. And the reason is, if we look at the scale, population in millions, the U.S. was 150 million. The world population was 2,500 million. Okay, so that is a lot more. So you have to pay attention to the scales. It does go from 1950 to 2000 on the x-axis, but the y-axis has a different scale. So the answer is no. Is Joe's observation correct? Why or why not? He says he doesn't think they grew by the same amount, but they grew at about the same rate. Look at the slopes. Okay, so Joe also ignored the scale as Callie did. The rate of change or slope is much greater for the world population than for the U.S. population. So the slope here, it went from about 2,500 to 3,000 in 10 years. So that would be, so this point here would be 2,500, 1950, 2,500. And this point, this is this point, and this point here is 1960, 3,000. Now remember, to find slope, we have to take y2 minus y1 over x2 minus x1. So if I take 3,000 minus 2,500 over 1960 minus 1950, then we get 10 in the denominator and 2,750 in the numerator. So it's a slope of 275. If I do the same over here, then this is the point. So I'm not going to write the points this time. It is 150. And then the next point, 1960, looks like it's about 180. So if I take 180 minus 150, the y's difference, and then take the x difference of 1960 minus 1950, then I get 30 over 10, or 3. So the slope of the U.S. was 3, or the rate of change was 3 million, and the rate of change of the world population was 275 million. So they did not grow at the same rate. Rate of change is your slope. Okay, part C. Use the world population graph to estimate the percent increase in world population from 1950 to 2000. Okay, so I brought the graphs in so we can do this easier. So we're using the world population. Okay, so we're using the world population from 1950, world population 1950 to 2000. So those are the values we're going to use. Excuse me. X is 1950, comma, y is 2,500. Okay, the other point is, come on, I changed to green, 2,000. Don't you love it when technology doesn't work? 2,000, 6,000. Okay, so we're going to use the world population graph estimate the percent increase from 1950 to 2000. The percent increase, remember, using the formula. So we need to remember the formula for percent change. And that is percent increase in this case. That's a change in the percent. It's new minus original divided by the original times 100%. So the new value is 6,000 minus the original value, which was 2,500, divided by that original 2,500 times 100%. So 6,000 minus 2,500 is 3,500 over 2,500, which these reduce. And 5 will go into 35 7 times, and 5 will go into 25 5 times 100%. 5 will go into 7 one time with a remainder of 2. So if I do this long division, 5 goes into 7 once with a remainder of 2, so it's 1.4. But when I multiply that by 100%, that moves the decimal 2 places to the right, so that's 140% increase. Okay, so now it says to use the U.S. population graph to estimate the percent increase in the U.S. population. So we're going from 150 up to, what is that, 280? Let's call that 280. So this is the point 2,000, comma 280. And this is the point 1950, comma 150. So we're going to take 280, the new value, minus the original population value of 150, and divide it by the original, which is 150, and multiply that by 100%. Okay, so 280 minus 150 is 130 over 150 times 100%. So I get 13 over 15. So if I take 15 and divide 13 by it, then I get, let's see, 8 times 5 is 40. 8 times 1 is 8 plus 4 is 12. And I get 100. And 15 will go into 107 times. Or not quite 7 times. I'm over a little, so that's a 6. So when I multiply this by 6, 6 times 5 is 30, carry the 3. 6, that's 90. And it's 8.666 repeating. Okay, so if we just round that to 0.86 or 87, just by rounding, 0.866 repeating would round at 0.87 and multiply that by 100%, then the percent change is 87%. Part E says, how does the percent increase for the world population compare to that for the U.S. population over the same period of time from 1950 to 2000? Well, if you look back up here, I erased it, but it was 140% compared to 87%, so the world percent increased faster. World increased faster. 140% is greater than 87%. F, do the graphs above seem to indicate linear or exponential growth? So if I go back to these here, okay, they look linear. They look like a straight line. So I would say that they seem, so notice I would use the word seem. I would say they seem to indicate a linear growth. Okay. G. Write an explicit formula for the sequence that models the world population from 1950 to 2000 based on the information in the graph. Assume that population in millions in 1950 was 2,500 and in 2000 was 6,000. Use T to represent the number of years after 1950. Okay. So what I would do here is, it's a function with respect to time. So f of t equals. So in order to find, and if it's linear, then it should be a linear equation. And remember, linear equations are y equals mx plus b, where m is my slope and b is my y-intercept. So if I go back to this graph, my y-intercept would be somewhere down here if it's a straight line. So it looks like it'd be about 2,000. Okay, so actually we're going from 1950, so we're not going to go back in time. So I want to use this value of, oh no, let's use this value here of 2,500. Let's make the graph start here, and that'd be our y-intercept, if you will. So 2,500 is my b. So I would say b equals 2,500. And we need to find out what m is to finish this formula. So we have f of t equals some rate of change times t plus 250. So all I'm missing now is my leading coefficient. How do I find the slope between 2 points? Well, it's y2 minus y1. Okay, so our years are x. These are our x's. This is x1 and this is x2. And our population are my y's. That's y2, and this was the population here, y1. So I take y2 minus y1, 6,000 minus 2,500 over 2,000 minus 1950. $6,000 minus 2,500 is 3,500, and 2,000 minus 1950 is 50. So this 0 will cancel with that 0, and 5 will go into 35 7 times with that 0 there, so 70. 5 goes into 350 70 times, so my equation will be f of t equals 70t plus 250, or that's 2,500. B is 2,500. Forgot my last 0. So there's the answer. Okay, mathematical modeling exercise 2, world population. How is this graph similar to the world population graph in mathematical modeling exercise 1? Okay, well, we're talking about a number of years between 1,700 and 2,000 this time. And we're talking about population in millions. So they are the same because we're talking about certain years and populations. Okay. And how are they different? Well, this is growing at a slow rate, then all of a sudden it starts growing faster. So this is exponential. So a thorough, complete answer would say this graph uses the same vertical scale as the one for world population mathematical modeling exercise 1. The graph is different in 2 ways. One, it shows years from AD 1700 through 2000 instead of 1950 through 2000. And 2, the graph itself shows that population growth took an exponential turn in approximately 1850. Okay, so I'm not certain I would agree with that portion though. It does look linear here, but exponential growth does start slow, so it's not going to be linear for a period of time and then turn exponential. It is going to be exponential the whole time. It's just that exponential growth occurs slowly at first. B, does the behavior of the graph from 1950 to 2000 match that shown on the graph in mathematical modeling exercise 1? So 1950 is right here and 2000 is right here, and we went from 2,500 up to 6,000. And when I look back at this graph here, 1950, we went from 2,500 to 2,000 up to 6,000. So this line here, it seems to be straight, just going between those 2 years, and here appears to be straight going through those 2 years. This looks like a steeper slope, but it's the same values. So it's going to be the same rate of change. 6,000 minus 2,500 over 2,000 minus 1950, and that will give us a rate of change of 70. So yes, both graphs show that the 1950 world population was about 2,500 million. Then that of 2000 world population was just over 6 million. Part C says, why is the graph from mathematical modeling exercise 1 somewhat misleading? Well, the graph in the mathematical modeling exercise 1 makes it appear as if the world population has grown in a linear fashion when it has really grown exponentially if examined over a longer period of time. Okay, part D. An exponential formula that can be used to model the world population growth from 1950 through 2000 is as follows. F of t equals 2,519 times 1.0177 to the power of t, where 2,519 represents the world population in the year 1950, and t represents the number of the years after 1950. Use this equation to calculate the world population in 1950, 1980, and 2000. How do your calculations compare with the world population growth shown on the graph? So in order to answer this question, our t is 1950, so I say f of 1950 equals 2,519 times 1.0177 to the power of t, which is 1950. Okay, so I just need to make one small change here. When I plugged that value in, the number was ginormous, so I realized I had made a mistake. And we're talking about 1950 being the beginning, so that's year 0. And as it says, use the equation to calculate the world population. T represents the number of years after 1950. Well, how many years are after 1950? 0. It is 1950. So this to the 0 power is 1, so f of 1950 equals 2,519. F of, let me do a different color, f of 1980 equals 2,519 times 1.0177 to the, and 1980 is 30 years after 1950. And when I enter that in my calculator, I get 4,264. And then f of 2000 isn't really, and I shouldn't call these f of 1950 and f of 2000. And this should be f of 0, number of years after 1950. This should be f of 30. And the last one should be f of 50. 2000 minus 1950 is 50 years after 1950, so it's f of 50 equals 2,519 times 1.0177 to the power of 50. And when I plug that into my calculator, I get 6056.4. Okay, so E says the following is a table showing the world population numbers used to create the graphs above. How do the numbers in the table compare to those you calculated in part D? So f of 0 is 1950, so if I bring this down, it is equal. F of 30 is 4,264, and we're at 4,435. So we're a little bit below, but fairly close. And then finally, f of 50 is 2,000, we're at 6056, they're at 6070. So our calculation is a little bit less than the graph, but it's fairly close. It was exact at 1950, but then it was a little off as we went down the table. F says, how is the formula in part D above different from the formula in mathematical modeling exercise 1? What causes the difference? What formula most closely represents the population? Okay, this is a lengthy answer. The formula in mathematical modeling exercise 1 part G is linear, while the formula in part D above is exponential. The growth rate in the linear formula is a fixed 70 million increase in population each year, whereas the growth rate in exponential formula is a factor of 0.0177 or 1.77%. An exponential equation grows by a constant factor each year, while a linear equation grows by a constant difference each year. The exponential equation offers a more accurate model since the projected population numbers using this model more closely match the actual figures. Okay, exercise 1. These are exercises. Pause the video, see if you can do them, and then come back and check your answers. Okay, the table below represents the population of the United States in millions for a specified years. In 1800, in 1900, and in 2000, U.S. population in millions in 1800 was 5 million. In 1900, it was 76 million. And in the year 2000, we were up to 282 million. A. If we use the data from 1800 to 2000, create an exponential equation representing the population, we generate the following formula for the sequence, where f of t represents the U.S. population and t represents number of years after 1800. So f of t equals 5 times 1.0204 to the power of t. Use this formula to determine the population of the United States in the year 2010. So f of, and t represents what? Years since 1800. So 2010 minus 1800 will be our t. 210. So I want f of 210 equals 5 times 1.0204 to the power of 210. Okay, when I put this in my calculator, I got 347.24. No, 0.35. So the population in 2010 will be 347.35 million, or 347,350,000. B says if we use the data from 1900 to 2000 to create an exponential equation that models the population, we generate the following formula for the sequence, where f of t represents the U.S. population and t represents number of years after 1900. So the first formula here was calculating a formula for these 200 years, but now we are focusing on just the last century. So the formula f of t equals this. We want to find the year 2010. That's years after 1900. So my t is going to be 2010 minus 1900, and that's going to be 110 years. So I want f of 110 equals 76 times 1.013 to the power of 110. Okay, and I got 314.67 million, or 314,670,000. So in the year, so if we're using the formula from 1900 to 2000, and we want to estimate the year 2010, we're actually lower because the rate of change is not figured in from the 1800s to the 1900s. C says the actual U.S. population in 2010 was 309 million. Which of the above formulas better models the U.S. population for the entire span of 1800 to 2010, and why? So we have 309 million, and when we calculated these two values, we had 314 with this formula, and we had 347, and the actual was 309. So which one is closer? Well, 314 is closer to 309 than 347 is, so the formula from the year 1900 is a better representation. So it says the formula in Part B resulted in a closer approximation of the 2010 population. Although the population of the U.S. is still increasing exponentially, the rate has slowed considerably in the last few decades. Using the population from 1800 to 2000 to generate the formula results in a growth factor higher than the rate of the current population growth. Okay, so we have slowed down in population growth. D says complete the table below to show projected population figures for the years indicated. Use the formula from Part B to determine the numbers. So in calculating this, the way I did this is in my TI-84 calculator, I went to y equals, and we are using the formula from Part B, it says. So if I go back to Part B, we're using f of t. So in y equals, that's what f of t is, in your calculator, in the y equals screen, puts this formula, and then when you hit second table set, then you change your independent variable to ask, and then when you hit second graph, you can actually plug in the values of the table to quickly fill this in. So I've already done that, so I'm going to put in 2020, but remember it's years since what year in Part B? Okay, so we're going from 1900. So what I'm really doing here is taking 2020 minus 1900, and I get 120. So t equals 120 for this one. And t, or add 30 to that, that is t equals 150, and this is t equals 180. And when I look at my table and enter those, I get 358.05. 2050 would be 527.21. And then when I plug in the 180, I get 777.17. E says, are the population figures you computed reasonable? What other factors need to be considered when projecting population? Okay, these numbers do not necessarily take into account changes in technology, efforts to reduce birth rates, food supply, or changes in life expectancy due to disease or scientific advances. Students may come up with a variety of responses. So there's many other possible reasons for this. Okay, we could have a major catastrophe or something like that. So number 2, the population of the country of Oz was 600,000 in the year 2010. The population is expected to grow by a factor of 5% annually. The annual food supply of Oz is currently sufficient for the population of 700,000 people and is increasing at a rate that will supply food for an additional 10,000 people per year. Write a formula to model the population of Oz. Is your formula linear or exponential? So since we're talking about population, we can use the letter P with respect to time. So P of t equals. Okay, now remember we always have an A times B to the power of something. That is a formula in exponential growth. So P of t equals, so what's my A? It's my original value, 600,000. Okay, my rate of change is 5%. That's 1, so it's going to increase 5%, so that's 105%, or 1.05 is my B. And that is going to be to the power of t. So there's my equation. And it doesn't matter, since there's only one thing in the parentheses, where the variable goes does not matter. Okay, and this formula is exponential. Part B says write a formula to model the food supply. Okay, and is the formula linear or exponential? So looking at the food supply now, our starting value A is right here, and it will increase at a rate with that will supply food for an additional 10,000 people per year. Okay, so that's increasing at the same rate. That is my increasing rate every year. That rate does not change. This is going to be linear. So my formula is going to include 700,000 and a rate of 10,000 with respect to time. So I would write food supply, or F of T, is going to equal that 700,000 that we started with, which is our B or our Y intercept, and we're going to add that to the 10,000 constant rate of change with respect to time. So it's linear. 10,000 times T plus 700,000 if you wrote that in standard form. C says, at what point does the population exceed the food supply? Justify your answer. Okay, so what we need to do is find out where these two are equal. Because if I have an exponential growth function, let me do it in the right color. So my last formula, I'm just trying to explain this visually. This formula here, exponential growth, without using any form of accuracy, I'm just going to explain to you what they're talking about here. So the population growth is exponential, like so. And the food supply is linear. So that's going to have a rate of change that's constant with a straight line. Okay, so this line could be anywhere. It could be here, like so, or anywhere like this, where it crosses. And at what point does the population exceed? So it's probably going to be somewhere around here. So there's the food supply is sufficient. This is the population. Food supply is greater than the number of people. So this means that there's enough food to feed this number of people. But at this point right here, there's exactly enough food for the number of people. But once I get to this point up here, there are too many people for the amount of food. So that's what it would look like if we graphed it. So at what point do these occur? Well, we want to know where the two equations are equal. Okay, so this is what our equation would look like, and we would have to solve this for t. So in this case, I would want to get all of my t's on one side and all of everything else on the other side. But the only problem with this is an exponential function. And in order to solve an exponential function, we have to do the inverse operation, which is a logarithmic function. And we haven't done those yet. So the only other option I have is to do a table. Okay, so I'm going to open up my on-screen calculator rather than just say what I'm doing. And I'm going to go to y equals, and I'm going to type in the two formulas. One is 600,000, parentheses, (1.05t), 1.05 to the power of t, but we're just going to use the x here in this case. Okay, and now when I hit graph, we aren't going to see anything because there's no values between 0 and 10. And notice it's still working there. So if I zoom out, that'd be 3. I'd have to keep zooming out before I could see it. Zoom. And if I hit zoom fit, we might be able to see it. Zoom fit is zoom 0. And when I graph that, now we finally see it. Okay, so there is what it looks like graphed. It's exponential growth. And now I'm going to go to y equals, and on y2, I'm going to put 700,000 plus 10,000 x, and graph that. And there are our two lines. So this is the value where they crossed. This is the food source growing linearly. This is the population growing exponentially. I want to know at what point will our food supply run out, or our population exceeds food supply. So it's at this point right here, that's the population going above the food supply. So I can now say, hit second, and the blue here, see how the button's blue? That means that it's going to command this. So if I use the trace button, second trace is calculate, and that's what I want. I want to find out where they intersect, so I'm going to hit 5, enter. And then it says curves, first curve, second curve, third curve. So you just hit enter 3 times, and it's going to tell us that x is 4.4 and y is 744,122. This is the number of years, and this is the population. So that's after 4 years. So at 4 years we were okay, but it's after 4 years. So sometime during 2015, we would run out of food. Now D says, if Oz doubled its current food supply to 1.4 million, would shortages still take place? Explain. Okay, so that means our food supply starting at 700,000 now would become 1.4 million. Would a shortage still take place? So what I want to do is go back to my calculator and change my equation. And instead of being 700,000, my food supply is now 1.4 million. So instead of 700,000, I'm going to do 1,400,000. And then if I want to insert, I hit second and see the INS above delete, second, insert a 0. And now that is 3 zeros, there's 1,400,000. And now I hit enter. And now I look at the graph. So here's our population growing exponentially. Our linear function, that would just shift it up to 1.4 million, increasing at a rate of 10,000 each year, but they still intersect, which means the population is still going to exceed the food supply if it grows 10,000 per year, starting at 1.4 million. And when will that occur? Well, we hit second, calculate, intersection, and hit enter 3 times, and it will give us this point here. So it's after 20 years. So in the 21st year from 19 or 2 let's see, what year were we going from? 2010. So after the 21st year. So it's still going to happen in the year 2031. I'm explaining it verbally. I'm not going to write the explanation. So part E says, if Oz doubles both its beginning food supply and doubles the rate at which food supply increases, would the food shortages still take place? Explain. So that means we're going to double our beginning food supply, which we've already done, 700,000 to 1.4 million, but now we're going to increase this 10,000. So our new formula is going to be food supply is f of t equals, and we're going to be 1.4 million, or 1,400,000 plus 20,000 t. That's our new formula. So I go to my calculator, I go to y equals, I come down to that formula, and I'm going to change that 10 to a 20, and then I'm going to hit graph. Here's our exponential growth. That has not changed. Our food supply increased to starting at 1.4 million, increasing at 20,000. So the slope is greater, but they still cross right here. So if I hit second, calculate my 0, which is 2, and hit enter 3 times, it says error bounds quit. Okay, second quit. Graph. Let me try that again. Calculate. Second, calculate. Intersect 5. And it's going to be at this value when the population is 186,400. Okay, 1,864,854. There it is. And it's 23 years after 2010. So it's going to be in the year 2034. Okay? All right, that is the end of lesson 6. These are very large values. Make sure you have a Texas Instruments calculator. Find an online one like I just did. Google it, and it's called WABIT, WABBITEMU. If you Google this, you'll find a video on how to install this calculator on your computer, and it's very helpful. So that is the end of lesson 6. Go do your problem set.